Hey everyone, so I wanted to make a quick video talking about the lung model. And before we talk about lungs, let's just talk about a beaker of water. So this beaker has some water in it. There it is. And maybe it's a 2-liter beaker. So that's pretty big. And in fact, it's some salt water of some kind. We'll just use some sodium chloride. And it turns out that in this 2-liter beaker, there are, we'll do 4 grams. 4 grams of sodium chloride. So this is the amount of salt. Whereas when we use words like concentration, we would take the amount and we would divide it by the volume. So this is amount over volume. So in this case, I'd have 4 grams divided by 2 liters. So I have 2 grams per liter. Okay, so often students have the right idea, but they'll say the wrong word, and like they might say, oh, I have 4 grams concentration, when what they mean to say is I have 4 grams of sodium chloride. But anyway, that's just a minor vocabulary lesson. Nonetheless, units will often help us follow our nose for the correct next step and stuff like this. Okay, so there's my beaker, and I just want it to be so much saltier. So it turns out I have this salt bath right here, which also has some salt water in it. But the concentration of this salt water is pretty dang high. There's 20 grams of salt, so again, sodium chloride, but we don't need to know that, per liter. So super concentrated. All right, here's what I'm going to do. I'm going to pour out 1 liter from my beaker. All right, so let's see. We got something like this, and then it's pouring out. All right, and so now here's my new beaker, and it's not nearly as full. It's down here. Okay, so there's 1 liter. So that was my first step. Now my second step is I want to scoop up 1 more liter, or I could pour in instead of scoop up 1 liter from the salt bath. So this super salty thing, maybe it has some kind of spigot, and I'm gonna pour out some of this stuff. In fact, 1 liter, and it's going in here. Okay, so I'll use green to say, all right, I add 1 liter, oops, not LL, 1 liter from my salt bath, from this thing. Okay, and now the question is, what is the new concentration of salt after that process? So I poured out 1 liter, then I poured in 1 liter. Okay, well, it might help to just keep track of the salt. So I start with, now I've already told you I have 4 grams of salt, but if I did not give you this number, let's get rid of that. And instead, I just gave you a concentration and a volume. Again, units help. So if I stare at this long enough, I might realize, well, if I have my 2 grams per liter and I multiply it by my 2 liters, that means I start with 4 grams of salt. Okay, now how much did I take away? Well, for every single liter, I'm going to take away 2 grams, and I poured out 1 liter. So 1 liter, I've taken away 2 grams. So, in other words, there's 2 grams remaining. Oops. Remaining after the pour. Okay, so that's these blue sort of model down here. But then how much do I pour in? So let's see. I pour in, well, it's a very salty solution, 20 grams per liter, and I pour in 1 liter. So I pour in 20 grams. So now my new total, I could think of it as start minus out plus in. So in this case, that's 4 grams minus 2 grams plus 20 grams. and that'll work, and you get 22. We could also just think of it as how much was remaining plus how much did I add. I added 20 grams. No matter how you want to think of it, as long as you have a way that makes sense, that's great. For the DTDS that we're going to use, sort of start minus out plus in, that's the typical form. Okay. But I have not yet gotten to the final concentration. What I have is the final amount. Okay. Now the concentration is just the amount divided by the volume. So my final concentration is 11 grams after doing this process. Okay, so if that makes sense, then, well, the lung model should make sense. Because instead of a cup of water, what I have are bubbles of gas or sacks of gas, just some old gas sacks. These are my lungs, okay? So here we go, got my, what are these, brachioli? I don't know, it's been so long since I had anatomy and physiology. All right, and my lungs have some volume, maybe about 6 liters. And maybe there's a chemical that I care about inside of my lungs. Maybe inside of my lungs, there's some carbon monoxide, that's some nasty stuff. Or hey, we're in Colorado, maybe there's some THC. Or maybe you're running into a burning building and we also care about CO2, in which case you probably care about both of these. In any case, the point is there's some kind of substance, okay? And there's millimoles per liter is the way we're going to measure this substance. And now if we're dealing with something like CO2, there's never no CO2 in my lungs. So I have some amount in my lungs, some concentration of CO2 to begin with. And I'll call that initial concentration C sub 0. And if we want a number, maybe my initial concentration is just 1 millimole per liter. So it's pretty low on the CO2. Okay? Now, instead of pouring out water, the analogy is I exhale. Okay? So I exhale. And maybe I exhale 1.5 liters of air. If I do that, that means that I've exhaled, well, let's see, I have 1 millimole per liter times 1.5 liters. Okay, liters cancel. I've gotten rid of 1.5 millimoles of CO2 in that exhale. All right. Now, if I was in a poorly ventilated kitchen, maybe there's more CO2 in the ambient air outside of my lungs. Okay, so the ambient concentration of CO2 is something our lung model calls gamma. And maybe this is up at like 10 millimoles per liter. Okay. So when I inhale, this is the stuff I'm inhaling. So I inhale the same volume, 1.5 liters. But in that volume, there's 10 millimoles per liter times 1.5 liters. Okay, liters cancel. I've just gained 15 millimoles of CO2. Okay. So my new concentration, or let's just do new amount, okay? New amount is the start minus what I breathe out plus what I breathe in. So I began with, let's see, 6 liters. Each liter had 1 millimole. So I began with 6 millimoles of carbon dioxide. I exhaled 1.5 millimoles, and then I inhaled 15 millimoles. All these units are millimoles, and my penmanship will just be terrible. There we go. All right. So my new amount is equal to, let's see, 6 minus 1.5 is 4.5, and add that, I get 19.5. So millimoles. So it just shot up, right? And that'll happen when you have a big discrepancy between ambient air and what's inside of your lungs. So, okay. Oh, I must have made a math error. Let's see. Oh, no, I didn't make a math error. Okay. So now that's the amount. But if I want the new concentration, I have to take the amount and I have to divide it by my volume. So in fact, let's add to this formula. Oh. So here's the idea. If I take my new concentration, well, that's my new amount over my volume, which is this over my volume. Okay, so let me get another page going. In this case, my new concentration is 19.5 millimoles divided by 6 liters, the volume of my lungs, and that would be all of this over 6 liters. Okay, so let's generalize this. And we can just stare at this idea here, all right, and just kind of start to realize where each of these three numbers come from. All right, so my new concentration, which, okay, let's start to introduce some labeling. I began and then I stopped. So I began with initial concentration. This new concentration I can call C1. So it's the new concentration after one breath of air. And in general, as I update, my new concentration is C sub t plus 1. Okay, so this is going to be my start amount, which I'll abbreviate as MAT, minus the amount that I exhale, my out amount, plus the amount that I inhale, in amount. Now those are all amounts. In order to get concentration, I have to divide by my volume. Okay. All right, so let's go through this one by one. Start amount. Do that one in green. Well, I have some beginning concentration, C sub t. And the units of C sub t, so typically this little box here means units of, but that's nothing we're going to quiz you on. It's just some typical math and science notation. Okay, so units of C sub t, these are millimoles per liter. If I want amount of substance, I had better take my millimoles per liter and multiply it by my liters. That way those go away. So I need to know, you could put down 6 liters, but if I want this to be more general, you need to think about how different people have different sized lungs. So in general, there's just some volume V. So V is the volume of the lungs. Oh, come on, pen, don't die. You were just fully charged. There we go, great. Of the lungs when full. Okay. All right, so that takes care of the amount of substance that I began with in my lungs. Now I need to figure out how much did I breathe out, the out amount. So minus, all right, so there's a new variable in town, W. This is the volume of exhale, inhale. All right, so we do not, when we exhale, we do not completely empty our lungs. This would actually cause a collapsed lung, which is very dangerous. You only exhale some fraction of that. But if we measure it in terms of volume, then I can just call this W. So W, like maybe, for example, in this problem, right? Here's W. It's 1.5 liters. And similarly, here was V. It was 6 liters. All right? So W is the volume that I exhaled, but I want an amount, right? This is saying an amount. Okay, so I have to multiply that by its concentration. So this is coming from my lungs, so it has the same concentration, and times the volume that I exhale. Okay, and now finally we're gonna figure out the amount that comes in. So plus, well, it's the same idea. So there's a volume, because the amount that I exhale in volume is the same as the amount of volume that I inhale. Okay, my lungs aren't going to change in size, but my source is different. So here, this is air in the lungs, but right here, gamma, this is the ambient air. This is air outside of my lungs, ambient air. All right? So computing these three quantities and doing the calculation would tell me the new amount of substance in my lungs. But I want new concentration. That's what this C is for. It's concentration. All right. So I need to take all of this and divide it by the volume of my lungs. All right. Now, this is a valid updating function. It's just we massage it a little bit algebraically to put it in a different form. So let me give myself a little bit of room. All right. And quick algebra comment. If you have a sum of numbers up top divided by some common number, you can just think of this as a over d plus b over d plus c over d. And I like to say that there's no such thing as division. And what I mean by that is anytime you have a division, what you're really doing is a multiplication by the reciprocal. So this entity here I can think of as a plus b plus c times 1 over d. And maybe it's easier in this form to realize that you have what I claim you have, because now I just have to distribute the 1 over d, and there we have it. Okay, so that's just a quick algebra aside. Let's get rid of that. All right, so I'm going to use that, and I have c sub t of v over v minus w c sub t over v plus w gamma over v. And hey, v, those go away. I have c sub t minus, and now we're going to group it with w over v, c sub t, plus w over v gamma. And if I look at what w and v are, so w is the amount of volume that I exhale and inhale with each breath, whereas v is the total volume of my lungs when they're full. So w divided by v, this is the fraction of air exchanged, more or less. Okay, so what do I mean? So if w over v equals 0.5, for example, that means half of the air in my lungs is what I exhale and inhale with each breath. So if my lungs were 6 liters, then w would be 3 liters. Half of the air in there is being exchanged. And similarly, I mean, that probably solidified it, but if it was 0.25, then this would only be 1.5. So that's the numbers I had before. So now a quarter of the air in my lungs is being exchanged. Okay, so this fraction, or another math word for fraction is quotient, we call Q. Okay, and it's just to reduce the number of variables floating around. So I can write this as c sub t minus q c sub t plus q gamma. And then because we just love algebra so much, we factor out a c sub t, and we write the final updating function like this, okay? Or I should say that's the right-hand side. Left-hand side is just c sub t plus 1, okay? So let's go ahead and see this in action. What's a good thing? All right. So if we had, let's say I walk into a room, and so for my class, I pulled up a chart of carbon monoxide levels and the side effects that you get when you're exposed to them. And with those side effects, in fact, let me see if I still have this table somewhere. I don't, but if you just Google carbon, you know what, let's just go ahead and do it together right now. Sorry, I should have thought of this ahead of time. But okay, so we're here, and so yeah, I was looking at what hay fever was. Okay, so we are curious about carbon monoxide and symptoms. We'll go with that, and I'm just going to click on images. Okay, and so this is measuring percent CO2 in the blood. I don't want that. Oh, last time it was so easy for me to find. Symptoms, exposure time. Here we go. All right, so they're measuring concentration in terms of parts per million, which is, it has units of milligrams per liter, I believe. And we use millimoles per liter. But if you take chemistry, you know you got to go grams to moles, moles to grams all the time. So they have slightly different units than we do. But the main thing I want to emphasize is that the symptoms depend on the amount of time you're exposed. So if I look at the 3,200 parts per million row, my symptoms in the first 5 to 10 minutes are not so bad. Headache, nausea, dizziness. But after 30 minutes, I'm going to collapse and become unconscious, right? Why is that happening? Why is that happening? So, all right, I don't feel like doing a unit conversion. So let's just pretend for a moment that the 3,200 parts per million, maybe this is something like, well, let's just pretend for a moment it's millimoles per liter. All right, so we'll just play pretend. It'll just help out. Now, if I walk into a room with very high carbon monoxide levels, so in other words, this is gamma, and maybe I begin, so my initial concentration is 0. There are no millimoles per liter of carbon monoxide in my lungs. All right, I'm just healthy like that, guys. Okay, so now typically an adult male like myself, my lung volume is something in like the 5 to 6 liter range. So since we were already dealing with 6, we'll just stick with 6. And maybe I just finished exercising and I have a pretty big, I think it's called tidal volume is actually the label given to this. It doesn't matter. So we'll say my Q is we'll just use a third. So that just keeps on going forever and ever. In other words, this is V and W is 2 liters, okay? So when inhale and exhale 2 liters, that's pretty ambitious. I was probably running ahead of time. I think it's more likely that your inhale and exhale is around 1 liter. It's really not that big. Okay, let's go ahead and do that. Let's just say that I'm relaxing. So it's around 1 liter. So it's about 0.15. Okay, so roughly 0.15. W, it's around 1 liter. All right. Okay, so here's my Q. Let's see, after one breath, so C1 is equal to 1 minus Q, C0 plus Q gamma. Okay, so this is 1 minus 0.15, so that's 0.85, and then C0 is 0, so I don't even actually care about that, plus 0.15 times 3,200. All right. So 0.15 times 3,200, well, if it was just 0.1, I would have 320, and then I have to add half of that, so that's 160, so then I get 480. So I get 480, and again, we're just pretending this is millimoles per liter. So within one breath, I'm going from 0 up to 480. All right. And we can play this out again. We can figure out, well, how much do I have by my second breath? So now I have 0.85, and then the concentration in my lungs is 480, plus 0.15, and the concentration in the environment is 3,200. Okay, so I'm not going to do this. You get whatever you get. But what I really want to talk about is a thought experiment. As time goes on, as I take more and more and more breaths, I claim the amount of carbon monoxide in my lungs approaches the same amount as the carbon monoxide in the room. But that takes time. I have to take my breaths. I have to swap out the air in my lungs with the air in the room. And with this beginning cup analogy up here, if I repeat this process, so I dump out a liter and then I refill from my sodium bath. And then I dump out a liter and then I refill from my sodium bath. And then I dump out a liter and then I refill from my sodium bath. More and more, the water in my cup is going to resemble the water in the sodium bath. Same idea with the lungs. More and more, the air in my lungs is going to resemble the air of the room I'm standing in. And this is why it takes time for side effects to occur. If you're only in that room for 1 to 2 minutes, you probably only took about 6 to 10 breaths. And so, yeah, you're going to be exposed to carbon monoxide and you're going to get a headache, but you're not going to be in danger of death. Oh, sorry, I'm looking at the wrong row now. Let's jump over to 32. So if I'm 5 to 10 minutes, okay, I think it's something like about 5 breaths per minute. So we're in the range of 25 to 50 breaths. And we'll get a headache. But after 30 minutes, so after 150 breaths, now we're losing consciousness, right? That's been enough time for the air in my lungs to look like the air in the room. Okay, so on an intuitive level, this is also telling us that we should expect the air in the room to become the equilibrium. That's what happens if I keep on breathing. But let's finish out this video by solving for that. All right, so my general lung model looks like C sub t plus 1 is 1 minus q, C sub t plus gamma q. I guess we'll put it in the other order, plus q gamma. All right, now if I want to find equilibrium, that means my output has to equal my input, but nonetheless the updating function occurred. So here we go. And I should get all of the variables that I'm trying to solve for to one side. So let's go ahead and subtract 1 minus QC star, 1 minus QC star. Okay, now this is going to look a little funny, so we'll write it out in steps. I'm going to distribute this one, or this negative one. So I have minus 1, and I want to distribute the C star. I'll have minus 1 C star plus Q C star. So that'll be my left-hand side. Maybe I should have done that in 2 steps. So let's take it back from one. I have C star minus 1 minus Q C star. And so what do? I could distribute the C star first if I want. So now I have C star minus Q C star. And then I can distribute the negative if I want, and then we're here. Okay. So anyway, here's my left-hand side. And my right-hand side, let's see, you've killed each other, and I'm left with Q gamma. But look at my left-hand side. I can do some cancellation. So what I really have is QC star equals Q gamma. And so long as Q is not equal to 0, which in order for Q to be 0, right, Q is W over V. V is the volume of your lungs. W is the volume of your breath. So you're not allowed to breathe in order for Q to equal 0. So that's not going to happen. So Q's not going to equal 0. So we don't even need to worry about, in fact, I shouldn't scratch that out. This is true. Q's not 0 because hopefully we're breathing. Hopefully we're alive. So I can divide by Q because it's not 0. And this says that the equilibrium point is gamma. All right. So we see this mathematically. We see this in the physical world of how it behaves. And I think that's a good spot to end the video.